In addition to providing us with an efficient system for approximating just intonation, two-dimensional regular temperaments also generate scales with very specific and useful melodic properties. These scales are called moment of symmetry scales. A moment of symmetry scale, or MOS for short, is defined by having exactly two different intervals that span one step in the scale, one large, one small, and by being derivative of a continuous chain of generators. That is, the same way the diatonic scale contains only a major and minor second, and can be derived from 7 continuous fifths repeated within the octave, all MOS scales must have only two types of second, and they must be derivative of a continuous chain of some generator repeated within some period. Since it has those defining properties, the diatonic scale is an MOS. As it turns out, our other standard Western scales are also moment of symmetry scales, including the pentatonic scale, whose two step sizes are the major second and the minor third, and the chromatic scale, whose two step sizes are the minor second and the augmented unison. Both are derived from continuous chains of fifths from the circle of fifths. Though we don't know for sure why historically we arrived so naturally at MOS scales, we can use that fact to theorize that other scales that share similar properties would be similarly fruitful. MOS scales are categorized by their number of large and small seconds. For example, the diatonic scale would be referred to as the 5 large, 2 small MOS because it has 5 major seconds and 2 minor seconds. Each MOS has what is referred to as a valid tuning range, the range of generator sizes over which that MOS is generated. As you vary the size of the generator across that range, the large and small steps vary in size compared to each other. At one extreme, the small steps shrink towards being non-existent, while the large steps take over the whole scale, at which point you reach an equal temperament equal to the number of large steps. At the other extreme, the small steps get larger and the large steps shrink until both are the same size, at which point you reach an equal temperament equal to the number of total steps in the scale. Outside of those parameters, the scales generated would no longer be of the same MOS structure. For example, the diatonic scale, aka the 5 large 2 small MOS, is valid with a generator ranging from approximately 685 cents to 720 cents. In the middle of these two, around 700 cents, you arrive at scales where the scale structure is obviously large, large, small, large, 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 small. As you approach 720 cents, however, the small steps shrink towards nothing until the minor second disappears completely and you get 5-tone equal temperament. Here is what that progression in generator size sounds like. Conversely, if your generator approaches 685 cents, your major and minor seconds approach each other in size until they are equal, at which point you have 7-tone equal temperament. Here's what that progression in generator size sounds like. The sizes and structures of the different MOS scales you reach given a period and a generator combination are determined by the ratio in size between those two intervals, though the intricacies of that relationship are beyond the scope of this video. To put it as simply as possible, the number of notes in each successive MOS scale, aka their cardinalities, follow a Fibonacci-esque pattern where each new scale's cardinality is an addition of two previous cardinalities. Also, the number of large and small steps in your new scale will match those two previous cardinalities. For example, when using a pure 3/2 and a pure 2/1, approximately 702 cents and 1200 cents, as our generator and period, we hit MOS scales after one note, which in this case is just octaves, then at two notes, a scale of one large, one small, a perfect fifth and a perfect fourth. Our next MOS is reached at three notes, aka 2 + 1, giving us a 2 large, 1 small MOS scale, including 2 perfect fourths and a major second. After that, we hit an MOS of 5 notes, aka 2 + 3, giving us a 2 large, 3 small MOS scale, which is our pentatonic scale. The next MOS is reached at 7 notes, which is 5 + 2, giving us a 5 large, 2 small MOS scale, which is our diatonic scale. And then 12 notes, 7 + 5, giving us a 5 large, 7 small MOS scale, an uneven chromatic scale. After that, the vague pattern continues on to 17 notes, 29 notes, etc. If you generate with a pure 6/5 and a 2/1 period, however, you arrive at a different combination of MOS scales, though they follow a similar pattern. They would occur at 1 note, 2 notes, 3 notes, which is 2 + 1, 4 notes, 3 + 1, 7 notes, 3 + 4, 11 notes, 7 + 4, 50 notes, 11 + 4, and so on. The closer two generators are in size, the more scale structures they'll have in common before they diverge. For example, when generating scales using a flatted 3/2 of 696 cents, as often happens in mean tone temperament, we arrive at the same MOS scales as when generating with a pure 3/2 until we get to the 12-note scale, which will instead have 7 large steps and 5 small steps, making it an uneven chromatic scale with a reversed structure. That scale is followed by MOS scales of 19 notes, aka 12 + 7, 26 notes, aka 19 + 7, and then the pattern diverges from then on. Here is what several alternative MOS scale structures sound like. Those are just several examples among an infinite number of MOS scales which are theoretically ripe for exploration. But how on earth should one go about playing these new musical structures if they can differ on such a basic level from our familiar scales? Certainly many of them would not be playable on traditional musical instruments. Next video, I'll be covering the most ergonomic way to represent these musical structures physically for musical performance.